Okay, so in this video we're going to do another example of the residue theorem, and essentially we're given this function and it tells us that C is an arbitrary curve and that f of z is analytic everywhere. What that means is that this function is analytic everywhere except for those 2 points that are the poles. So what are the poles that we have here? Well, we have to identify that we have a pole of order 3 here because that's to the power 3, and essentially we cannot really reduce this more because even though we could write this as z plus 1 3 times, this doesn't mean that we have 3 different poles of order 1 because in essence we have the exact same pole. So this wouldn't really count as 3 different poles, this just counts as a single pole of order 3. So that's just the main difference. If we cannot really factorize this into different factors, then essentially this is just a pole of order 3. And the value is z is equal, let's call this z1. z1 is equal to minus 1. And then we have another pole here of order 1. So n equals to 1. And let's call this z2 equals to 1. So those are the 2 poles. So what it means by analytic everywhere means that we need to take into consideration all poles and that all these poles are going to be included into a calculation of residues. So the first thing to do is to find the residue of this pole. So let's have, actually I'm going to start with this one because it's the harder one. So residue of the function of z, which is this whole expression, evaluated at minus 1. And this is going to be a pole for the 3, so that's going to be 3 minus 1 factorial times the limit as z approaches minus 1 of the derivative. So 3 minus 1, that's 2, so that's the second derivative of the expression. And we're going to have z minus 1, which is going to be z plus 1 to the power of 3 times this expression. So that's going to be z plus 2 over z plus 1, 3, z minus 1. And you can see that very easily these 2 expressions cancel out. So in the end, we're just going to take the second derivative of this expression. So the second derivative with respect to z of this, we can either use the quotient rule or we can use the product rule if we rearrange this as follows. So let's have z plus 2 times z minus 1 to the power of minus 1. So now we can use the product rule to evaluate this. So this is going to be equal to what? So the derivative of the first one is just 1. So that's going to be z minus 1 to minus 1. And then the second one is going to be the derivative of this, which is going to be minus this. So z plus 2 times z minus 1 minus 1. So that's going to be minus 2. And then if we rearrange this, we get z minus 1 minus z plus 2 over z minus 1 squared. So that's the expression we get. And now we're just going to take the limit as z approaches minus 1. So the limit of this as z approaches minus 1 is going to be the following. It's going to be minus 1 here plus z plus 2, sorry, it should be minus 1 plus 2, so 2 minus 1. And then minus 1 squared, so that's minus 2 squared. So we're going to have minus 1 on 2 plus 1 over 4. And this should turn out to be the following, minus 3 on 4. Because if we express this quantity as 2 over 4, oh, actually, this should be minus 1 on 4, right? So we're going to have the following. Let me just erase this a little bit. Okay, so we're going to, so this is minus 1 over 4. Now we're going to find, and obviously we need to multiply this. We need to multiply this by this quantity here. So that's going to be 1 over 3 minus 1. So 2 factorial is just 2. So we're going to multiply the denominator by 2. So the residue in the end is going to be equal to minus 1 over 8. So that's the residue for this pole. And now we can proceed and find the residue for the next pole, which is going to be this one. So that one should be a little bit easier. So let's let's have the second one, residue of f of z evaluated at 1. And now we have an order 1 ball, and the value is 1. So this is gonna be a little bit simpler to evaluate. So we're gonna have 1 over 1 minus 1 factorial, so that's just 1. So we're gonna take the limit as z approaches 1 of the derivative. So it's an order 1 derivative, so that means 1 minus 1 is 0, so the derivative is just going to vanish, and then we're gonna get the limit of the following function. It's going to be z minus 1 to the power of 1 times the function, which is z plus 2. Now I'm just going to write it this way, z plus 1 to the power of 3 times z minus 1. And these two terms cancel out, so in the end we're going to get, as z approaches 1, so that's going to be 1 plus 2, that's 3. And then here we're going to have 2 to the power of 3, that's 8, so that's 3 on 8. And that's going to be our second residue. So in the end, what we're going to have is the following. So our integral z plus 2 over z plus 1 cubed times z minus 1 dz is going to be equal to 2 pi I times the sum of the two residues. So in this case we have minus 1 over 8 plus 3 over 8, and then this is going to come out as, so minus 1 over 8 plus 3 over 8, that's 2 over 8, and that's 4 over 8, so that's 1 over 2, so I pi on 2 should be the answer. And that's just to show you a simple example of how to apply the residue theorem to evaluate an integral like this without having to go through the trouble of performing partial fractions, because you could use Cauchy's integral formula here, but obviously you would need to separate this denominator into two separate fractions, and then you would need to use the derivative form of Cauchy's integral formula to evaluate this order 3 pole, and then obviously that will be a longer process. But in general, the residue theorem works really well for evaluating most complex integrals that look like this, or you could have any function at the top really, and you should be able to evaluate this.